So good afternoon, ladies and gentlemen. Welcome to our regular morning seminar. And it's a great pleasure for me to introduce my longtime colleague Ondřej Suchý, and he will give a talk about parameterized algorithms on TSP.
Yeah, so first of all, I'd like to say that this is based on an invited talk at Czechoslovak Graph Theory Conference. So it should be a bit more like survey and a bit more like inviting. So there will be two exercises for the audience and an interview. So yeah, so what is a TSP so that we are all on the same page? So the input is an undirected graph with some weights on edges, which represent lengths of the edges. And the task is to find a Hamiltonian cycle, which is a cycle that contains all the vertices of the graph, such that the cycle has the minimum length counted as the total sum of weights of the edges on the cycle. Right? So this is like a map of Czech Republic, let's say, and these are the like area centers of Czech Republic. We have like 14 areas in Czech Republic, and these are the 13 centers of them. And yeah, so this could be some good tour for that. Okay, yeah. So yeah, so this is like Hamiltonian cycle in this graph. Okay, so yeah. So what is known about that? So this problem is obviously NP hard. It's even hard to approximate to within any reasonable factor. And this can be shown by a simple reduction from Hamiltonian cycle, and it's NPO complete, speaking about optimization problems. So I will not delve into this. A very popular case is a case where the weights satisfy triangle inequality, which means that the graph is complete, and for every triple of vertices, we have that going from X to Z, and from X, from Z to X and from X to Y is what I'm saying. Going from X to Z is at most of the same length as going from X to Y and from Y to Z. Like going over something is at least as long as going directly. Okay. And for this special case, there is a famous 1.5 approximation due to Christofides and independently due to Serdyukov. And since then, it was long time open whether you can do something better until 2021, when some group of authors announced that they can shave off 10 to the minus 36 from the approximation factor if you sacrifice deterministics, because it's only randomized, okay? So it's in expectation they shave off this 10 to minus 36. Okay, so yeah, and it cannot be approximated better than 117 over 116 unless p equals np. Okay, so this for this case, but you see people are still like making research on this problem. Okay. Another special case, even more specialized, is Euclidean TSP, where the vertices are points in some d-dimensional space, and the weight of each edge is simply the Euclidean distance between the 2 points. And so this would be almost like the first example that I showed you, with just like if you are going by car, it's not just the distance what matters. So yeah, it's like, yeah. But for this special case, when you can have 1 plus epsilon approximation for any epsilon which is positive and in any dimension, and if the epsilon and the dimension is fixed, you can do it in roughly n squared times logarithm of n. So that's like independent of the factor. So yes. So what are parameterized algorithms? Yeah. So in parameterized algorithms, you're given a parameter together with your input, and your task is to develop an algorithm such that the exponential part of the running time depends on the parameter, and the dependence on the size of the input is a polynomial of constant degree independent of the parameter. So this is fixed parameter. This is called fixed parameter tractable. And then we also have a class of xp, which is just that. It's polynomial for every fixed k, but the degree of the polynomial can grow with growing k. Okay, so yeah, I guess most people know that. I should probably go fast over this one because this is just an example of parameterized algorithm. So if you ever heard about vertex cover, where you are given an undirected graph and the number k, and the question is whether the graph has a vertex cover of size at most k, then for this one, vertex cover is such that from each edge you either take one endpoint on the other one. For this, you have an algorithm which is in n to the k plus 2. That's trivial. Just try every k tuple. So this would put this problem into XP. But this is impractical. If you have 1,000 vertices and your k is just 3, this is already impractical. So an FPT algorithm which you can produce for this one is like 2 to the k times n squared. This is easy to do. And just as long as there is edge, take either this endpoint or that endpoint and put it into the solution. This is 2 to the k times some n squared. And this is still usable even with this 1,000 vertices, even if your k is something like 15. So that's to see what's the difference between FPT and XP. So now, and the size of the solution is called the standard parameter for parameterized complexity. So what is the standard parameter for our problem, namely TSP? Well, the size of the solution is n, the number of vertices of the original graph. But it's not really the size of the input, because the input can contain big numbers. So in fact, you can have trivial solution, which is like n factorial times the size of the input. Well, even if you have large numbers, summing them, you can do it in linear time in the size of the input. But the size of the input is not the same thing as n. We are using n as a parameter, although we never really stress that. So in the rest, I will ignore that. Like summing some numbers might take long. So like for this parameterization, the famous algorithm is help card dynamic programming. I will present it on the next slide, and it improves the running time to something like 2 to the n times n squared. And like as I said, people are still doing research on this problem. So in May of this year, someone announced that he can shave off from this running time something which is sub-polynomial. I don't know how much interesting is that. It's still weren't published anywhere, so I doubt a bit. And you can also ask what you can do if you require that the space that you take is polynomial, and then you have to spend 4 to the n roughly to solve the problem. Okay, so let's get to help and card dynamic programming, so that at least you learn something maybe. How to do it? Fix one of the vertices, and then for each subset of the rest of the vertices, and for each vertex from this subset, you save in a table the length of the shortest path that starts in the one fixed vertex, traverses the subset that you have chosen, and ends in the vertex that you have chosen. So something like what you see down there on the figure. Now, how to compute it? Okay, if you have just one vertex in the subset, then it's just the length of the edge from the fixed vertex to this vertex. And if you have more than one vertex, then you basically try to guess what was the previous vertex on the path. So before you came to S, you must have ended up in some previous vertex, and the subset was exactly like everything except for the last vertex, and you take the minimum over all the previous vertices. And finally, you output like the minimum over, like, you visited all the vertices, and this was the last one, and you connected with the first vertex, which was fixed. So this is half-car dynamic programming. I hope you understood it well, because here comes the first exercise. So it's about thinking outside the hull. Yeah, students that attended my course already have seen this exercise, so I'm sorry about that. Yeah, so for Euclidean TSP, there is an algorithm that works in time 2 to the h times h squared times n, where h is the number of points that are not on the convex hull. So that's why I'm saying thinking outside of the hull. So and this is your exercise. So if you want to drop off, you can think about how to solve this exercise. Okay. So yeah. Okay. So these were. So this is also to show you that the parameter can be like something that you're not very used to think about. So the number of points that are not on the convex hull is an interesting parameter for TSP. Okay. So yeah. To get to another parameter, let's talk about a popular heuristic for TSP, which is called link-Kernighan. So this works as follows: start with some Hamiltonian cycle. I mean, you usually do it in a complete graph, so finding some cycle is easy. And then you search for a better cycle locally, which means in something which is called k-opt neighborhood of the original cycle. If you succeed and find a better cycle, then replace the original one with this one and repeat it. So like locally, you try to improve your cycle. And once you fail to find a better cycle, output the one that you have. So what does it mean, k-opt neighborhood? We also call it k-edge neighborhood. We say that the new cycle is in the neighborhood of the old cycle if it can be obtained by removing k-edges and adding another k-edges. So like this is like distance 2, or like 2 edge modifications from the original one. This is like 3 edge modifications from the original one. Okay. So now what we can have a look on is like this one step of this heuristic, and like try to solve it like better or optimally. So what is the task of one step? So we are given an edge-weighted graph with some set of vertices such that the identity, like taking v1, v2, and so on, is a Hamiltonian cycle. It's the given one. And some integer k, which specifies the size of the neighborhood. And the question is whether there is an improved Hamiltonian cycle within the neighborhood of the identity. Well, but in this step, we actually need to find it, right? So that we can continue. So it would be better to specify it as a task of finding one. So if we take it strictly, one interpretation of what we are doing is trying to really find something better in the neighborhood. So the strict task would be to find an improved cycle within the k-neighborhood of the identity. If there is any, you can report there is none, no such cycle. Okay. But in fact, this is too strict, like interpretation of what we are doing in this step. We actually, like, what's important for us is to find a better cycle, not that it is in the neighborhood. So a permissive task is to find any improved cycle anywhere, given that there is a better one within the neighborhood. And there are problems for which the strict task is really hard, but the permissive task is easy.
Wait, so permissive means somebody promised you that this exists?
No. It means that I allow you to report a cycle that is not within the neighborhood. Just I'm happy with any improved cycle, but you should be able to report an improved cycle if there is one in the neighborhood. But the cycle that you give me doesn't have to be in the neighborhood. So in particular, if the neighborhood specified is this circle, I am fine if you are able to search a larger neighborhood and find an improved cycle in larger neighborhood, like this spell. Okay? But in the strict, I insist on this new cycle being within the neighborhood, which might be hard to check. Or hard to achieve. Okay, so from now on, I will always consider only the permissive tasks because that's be reasonable. Okay, so what about this permissive task? How fast can we solve it? Okay, if we are to change these k edges, this can be trivially solved in n to the k factorial times 2 to the k, like guessing the order of the parts that are left and like whether they are this way or the other way, or like something like that. You guess which edges to leave out, and yeah. So this is like XP. So what if I want FPT, f of k times n to the constant? Is it possible? That would be much better, right? I could search large neighborhoods in reasonable time. Unfortunately, this is not the case until FPT equals W1, as was shown by Daniel Marx. We have strengthened this result slightly by showing that actually you cannot improve the dependence of the degree of the polynomial much below k. You can shave off some logarithm and that's it. Or I mean, you cannot shave more than the logarithm unless, yeah, that's the right message, unless ETH fails. So yeah. So, but we were thinking about also different measures. So you can measure the distance between two cycles in many different ways. The one of the easiest ones is maximum shift, which measures how far any of the vertices have moved in the permutation of vertices that you are considering. This is called max shift. Then we define three operations like this. So swap basically swaps the vertex which was on position I to position j and vice versa. In terms of the edges, it looks like this. Then we have edit, which simply moves like I to the position j. And then we have reversal, which reverses the part between j and I. It's traversed in the opposite direction. And if you allow to apply k of these operations, you arrive at swap, edit, or reversal of k neighborhood. We also consider this R swap and R reversal. It just says the distance for which I swap or reverse is not too far. It's limited by this R. Like to swap is a transposition local. So what are the relations between these distances? So there is some definition, but I don't think that it's important that you read it. I just want to tell you, like, if two cycles are k swaps apart, then they are also like 2k edits. That's what the graph means. If they are k edits from each other, then they are 3k edges from each other, and so on. Yes?
Can you do combinations of swaps, or is it not like 2 swaps and 3 edits, or is it not?
we did consider that. Okay. Yeah. Maybe like once you see this picture, like okay. So what's true is that if something which is above is solvable in FPT, then everything below it is also solvable in FPT. And the other way around, if something is hard already here, then everything above it is hard. So there is an old algorithm by Balázs which shows that with respect to max shift, the problem is FPT. So this is green. So everything what's below is green. Then Marx showed that edge, which turns out to be the same as reversals, is hard, and we were able to show that already swap distance is hard for general graphs. So what we did next is put in more graph theory, because I was to present this on a graph conference, so some structure should be in. So what about planar graphs? In planar graphs, we can show that if there is an improved cycle, then there is an improved cycle such that all the changes happen in a small neighborhood of a vertex, neighborhood in the graph sense. Like every change happens in distance at most some 3k from some vertex. And the reason for that is that if you have two swaps that don't influence like neighboring vertices, then you can do them independently. And if you have many changes that you can do independently, at least one of them brings you the improvement alone. Like that's basically the point behind this theorem. So if you know this, then if again I have a local TSP on planar graphs and a vertex, and the question is to find a best tool that differs from the given one only in some neighborhood of some vertex, like k neighborhood of some vertex, then you can find such best tool in time which depends like 2 to the k times n plus n cube. And the reason for that is if you take a small diameter neighborhood of a vertex, then it has bounded treewidth, and you can use dynamic programming over bounded treewidth on this neighborhood, as you will see later in the talk. So based on that, there is a permissive FPT algorithm for local TSP parameterized like by the distance in terms of swaps and add-ins. So for swaps, it's hard in general graphs and easy for planar graphs. That's the message. How about the edge neighborhood, and why does this not work on edge neighborhood? Like consider this graph. This graph only has 2 Hamiltonian cycles, and like this, and these changes that you have to make between these 2 Hamiltonian cycles are far apart in graph sense, but they influence each other. There is no change like in between these two, which would only change it locally. So the approach that we used for the other measures doesn't work for this measure. So I want to also survey some results for small distances. So we already know that there is no algorithm that would improve significantly, but actually there is an algorithm that improves the running time, like improves the exponent to 2/3 basically, plus 1. And this gives Kubik's algorithm for 4-opt neighborhood. But even if you, for 3-opt neighborhood, if you were able to go below and like cubic time, this would mean an improvement for all pairs shortest path which is believed not to be possible. Okay. And there is, in fact, what you can do is n to the 1/4 times k plus some lower order terms for general graphs, and you can do n to the 23/135k plus some lower order terms for graphs of constant maximum degree. And they also showed that the lower bound still applies even to graphs of maximum degree 3. So you cannot improve the exponent below linear, or significantly below linear. Okay, so how much time do I have? Okay. Okay. I don't have that much, but okay. Yeah. So let me now. I have promised, like I have already talked about TSP, about parameterized algorithms, but the title also promises to speak about generalizations. So let me now introduce some generalization. So this is called Waypoint-Rotic problem. Here you are given, you're still given an undirected graph, but now you're given a set of terminals, like interesting points in this graph. You still get edge weights, but now you also get edge capacities, and you get some budget. And the question is whether there is a closed vault of total weight at most the budget that traverses each of the interesting vertices, each of the terminals, at least once. It can traverse it more times. And such that for each edge, the number of times that the closed vault traverses the edge is at most the capacity of the edge. And we also define subset TSP, which basically only doesn't have the edge capacities, or they are set to some big numbers so that we can ignore them. And what is called graph TSP in the approximation community is just this problem if every vertex is a terminal. And I will, from now on, I will call it just TSP. Okay, but now we can visit every vertex more times. We are allowed. That's basically the check. And yeah, so here is some solution for the given instance. So this one of the edges is drawn as double edge. That means that it has capacity 2. You will see shortly that capacities 1 and 2 are enough. But, okay, yeah. So what you should note is that this definition has triangle inequality included, like by definition. It's implicit in the definition. You don't have to say like I have it. You have it by definition. And there is 1.4 approximation for graph TSP. It's better than this Christofides-Serukov for general triangle inequality. Okay, so there are some basic observations. First of all, I ask you to produce a closed vault, but instead you can produce what I call Eulerian multi-subgraph. So like you take all the vertices which were traversed by the closed vault, you take all the edges which were traversed, but you take it as many times as you traversed it, which this makes it like it's not a subgraph of the original graph, it's a multigraph, which okay. Yeah, and you can easily see that it is Eulerian, that it's connected and it must have even degrees. On the other hand, if I give you this submultigraph, you also get the closed vault. It's equivalent that you search for a submultigraph or a closed vault. So here is the lemma that we use frequently in our result. And it says that an optimal solution uses at most 2 and minus 2 edges in total. In particular, whenever I look on some subgraph, it uses at most 2 times the number of vertices of that subgraph minus 2 edges on that subgraph. And if you look on a subgraph of 2 vertices, it uses also like 2 times the number of vertices minus 2, which is like at most 2 times this edge, right? And this is another exercise for you. Okay, so and based on this lemma, we assume that the capacities of the edges are just 1 and 2. Okay. Next, I want to speak about treewidth, which measures the structure, and it measures how far is the given graph from being a tree. Sometimes people say that it's how close it is, but like the number grows like with being far from being a tree. Okay, and a nice definition which doesn't give you any intuition at all is that it's a minimum clique number, maximum clique number in minimum clique number in a chordal subgraph of the graph, meaning out of over all chordal subgraphs of the given graph, I take the one which is the minimum clique number, and then at the end I subtract 1 so that it's more complicated. But I want you to understand what the treewidth is, so I will give you another definition in a second. So treewidth indicates how much the graph is suitable for some kind of dynamic programming, tree-like dynamic programming, and it can be defined using boundaried graphs which have distinguished boundary, and only the vertices on the boundary can get neighbors later on in the later stages of the construction. And you can think about boundaried graphs as about rooted subgraphs. So if you ever did a dynamic programming on a tree, then you probably saved some information about what's going on in the root of the tree. And that's what the boundary does for you. You're saving the information about what happens on the boundary and forgot everything about what's going down there in the tree. So definition of treewidth by operations: a graph has treewidth at most t if it can be built from empty boundary graphs by the following operations. First operation is you introduce an isolated vertex and put it into the boundary. Another operation, you introduce an edge and between 2 vertices of the boundary. Third operation is that you forgot a vertex, or like say this vertex is no longer part of the boundary, but it will still be in the graph, but it's no longer part of the boundary. And the fourth operation is that you have 2 graphs which have the same boundary. The boundary doesn't contain any edges, and you stick them together over the boundary. Like put the boundaries one on top of the other and stick them together. And you have to do that in such a way that the boundary always has size at most t plus 1. Yes?
Do you really need that you have no edges in the boundaries for the last one?
Well, you could do it without this requirement, but for my dynamic programming, it's better to do it like this, and you get the same thing if you could allow that, but you don't have to allow that to get all the graphs of boundary tree. Okay, so that's treated by operations. What I didn't say is that at the end we assume that the boundary is formed by one terminal vertex. That's specific for our problem already. Normally you expect the boundary to be empty at the end of the construction, and you get some construction tree, like how you use the operations and so on. This is roughly the nice tree decomposition of the graph. Okay, somehow corresponds. So, and I want to show you dynamic programming for that problem on this nice 3D composition, or based on the operations that you can do. I will not explain it to the very detail, but I want to show you some basic concepts of this dynamic programming. So the table is indexed by the stage of the construction that we are in. Like if you have the tree of the construction, like where you are in this tree. And then it's indexed by a subset X of the boundary. This is the set of vertices that will be visited. And then you have a subset L of the boundary, which represents the vertices of odd degree. Only those vertices will be of odd degree. And then there is a partition of the set X that represents the connected components. So how does it work? Yes, and if you take the set of visited vertices and the set of vertices of odd degree, this is what we call a presignature. And if you add also the partition of the set X, then we call it signature of the solution. And now let's speak about what is the partial solution. Partial solution is, didn't I say submultigraph previously? Submultigraph of the graph that we had so far. We call it a partial solution. Satisfies signature XLP if every already introduced waypoint is present in H, is visited. The intersection of this submultigraph with the boundary is exactly the set X. If a vertex has odd degree with respect to this partial solution, then it is in the set L, and in particular, it's in the boundary. And for every connected component, I should show you something. For every connected component, each of the components has some vertex from the boundary. And in fact, the intersection of the component with the boundary is exactly one of the sets of the partition. So basic DP is just for each stage of the construction. And for each signature, you save the minimum weight of a partial solution that satisfies the signature, and you get some runtime, which is roughly treewidth to treewidth times some other terms, and linear in the size of the input. You can improve it. And the basic idea behind the improvement, I didn't depict the set X, but this is like the partition. So these vertices are not used by the solution. But here, imagine that these are like the signatures of your solutions in this part of the graph. And what you really care about is whether these will be compatible with what is to come from the other part of the graph that you want to stick to that, which is the graph which is drawn here. It can also be like set in terms of the signature, like what the other part of the solution which is to come will do with the solution. And the thing is that at the end you want to have a connected graph. And if you look on these, although they have different signature, each of them, when combined with this signature, will give you a connected graph. Right? Because it will like connect the components of like the components of this will connect the components of this, form one big component. And whether it will be compatible or not only depends on which of the cuts that you can make on the boundary it crosses and which of them it does not. So in fact, you don't have to store all of them, but you have to make sure that for whatever comes from top, there will be something compatible in the bottom that you have stored. Right? So for each presignature, we store list of pairs of the partition and the weight. And it's enough to store something which is called representative set of the partitions. And there are something like 2 to the 3 width, many of them. in the smallest representative set. You can show that there is a representative set with this many partitions. You don't have to store more than that. And you can actually compute which of them are a representative set based on something like computing some basis for some cut matrix, which says like which cuts are crossed by this partition. But actually, for our result, we didn't have to go through all this machinery. There is a framework that is ready, and you can just use it. And it does all the standard manipulations with the partitions for you, and you don't have to prove again that this is representative after that and this. It does everything for you. It's like that. Yeah, it's like a box that you can use and don't need to know what is inside, which I just explained to you. So we use that to show that waypoint routing can be solved in 2 to the treewidth, or O of treewidth times n. And what I always like to say is that the previously known result of Emery and his colleagues use the same. Uses the same symbols in the time complexity as we do. Just the permutation is different. So yeah, and you cannot do significantly better unless ETH fails. But that's easy to prove based on Hamiltonian cycle having similar result. Okay, so that was the DP. I think we are almost getting to the end of the lecture. So I wanted to speak about kernelization. So I hope most of you, at least those that are able still to follow, know what is a kernelization. So so what is a kernelization? Is a polynomial time algorithm that reduces the size of the instance to something bounded in the parameter, and of course it preserves the answer. And it's known that a decidable problem, a parameterized problem, has a kernel if and only if it is FPT. But what we are interested in are polynomial kernels. What I can say is, if we look on the previous parameters that we have seen here, it's like local TSP for any of the measures that we considered, even on planar graphs, doesn't have polynomial kernels unless strange things happen. And for the waypoint routing, it's the case for the treewidth or tree depth or vertex integrity, which is defined here. I'll skip that. What I wanted to show you is a polynomial kernel with respect to feedbeck edge number. Feedbeck edge number, it's also known as Betti number or cycle space dimension, is the number of edges that you have to remove so that you obtain an acyclic undirected graph. And a graph with small feedback edge set number may look something like this. Again, these double edges represent the edges of capacity 2. Okay. There are some simpler rules that make sure that we are not in any edge case. And then there is a simpler rule which deals with vertices of degree 1. So kernelization is usually specified in terms of rules which say, if this appears in your graph, then do this and that with your graph. So here, if you have a vertex of degree 1, if it is not a terminal, then simply delete it. It's useless in the instance. If it is a terminal, but the edge which is adjacent inside it only has capacity 1, then there is no hope to find a solution. And otherwise, we just delete this vertex and make its neighbor a terminal if it wasn't before, and count like 2 times the weight of this edge. Like decrease the budget by this number. Okay, so this was easy. Then if you have a long path which is formed just by non-terminals, then you can just remove all internal vertices from that path and replace it by one edge which has the capacity which is the minimum of the capacities, and weight is the sum of the weights. That's also easy. There is no reason to stop anywhere on the path and do something more interesting. Either you pass through the path completely or not. And then there are like more complicated rules on what happens if you have a path formed by terminals. Like now there is no reason to have non-terminals on the path. So if you have two edges of capacity 1, then you replace it by, again, two edges of capacity 1. One of them has weight of one of the edges, and the other one has capacity of the rest of the edges. It doesn't really matter. If you have only one edge of capacity 1, then you replace it by this gadget. And if you have no edge of capacity 1, then you find the edge of maximum weight and replace it like this. And the reason to do it like this is if you sweep the path from left to right, then you can represent it here in similar manner, and it will cost you exactly the same thing. If you go the other way around, it's the same story. You can also do it on the new gadget. The more interesting stuff can be only done on the bottom two pictures, which is you go to the middle of the path, then turn around and go back, and then come from the other side, turn around and go back. This can be represented here like from going like from this side, you only turn already here, and from this side you come here and go back, and you can see that you pay exactly the same amount on both sides. And a similar thing here. And the final thing, which can be only done on the bottom part, is that you go completely the whole path to the left, and then go whole path to the right. And then on this gadget, you can do it also, and you pay exactly the same amount. Okay, so what does it do with our graph? Is that first get rid of all vertices of degree 1, which does something like this. Now you use the rule that removes all non-terminals from the path. Then you use the rule which takes a long path of terminals and replace it by this graph which has bounded number of vertices, and by some argumentation about the feedback edge set number of the original graph, you can, although this reduction can increase the feedback edge number of your graph, you can argue that it's still bounded by the original feedback edge number. Okay, yeah, so the resulting graph has linear number of edges, but the edges, the weights of the edges can be still large, and there is some result that you can use for that, and I will skip that. There is how you obtain kernel for TSP. I will also skip that because I think we are running out of time. I will skip all of that. You can see that, subscribe to our channel. This was already presented here by Vašek Blažek, so I'll skip this part and let me get to the summary. I want to skip this, I guess. So what you have seen is parameterized algorithm for local search for TSP, parameterized algorithm with respect to structural parameters. You have seen kernelization with respect to structural parameters. You have seen two exercises. And what are the open problems? So there are open problems concerning approximation. So if you could improve Christofides approximation more than to 10 minus, okay, then people would be interested. If you could improve help-car dynamic programming, people would be interested. But concerning our parameterized algorithms, so we still don't know whether there is an FPT algorithm for local search with respect to the edge neighborhood in planar graphs. We don't know whether this is possible or not. We don't know whether there is a polynomial kernel for TSP with respect to feedback vertex number, which means the minimum number of vertices that you have to remove such that your resulting graph is a forest. Even we don't know that in case that the forest is a union of paths after you remove the vertices. We don't know. And for subset TSP, I didn't speak much about subset TSP here, but we would be interested in polynomial kernel with respect to minimum number of vertices that you have to remove, such that each connected component of what you obtain is of constant size and it is a tree, like forest of small trees. And that's all from me. Thank you.
Questions? Maybe if you can go back to the local TSP, the graph of operations, that when it's easy, when it's hard.
I can try. No. It was this one. Previous one.
The same one.
Yeah, it's the same one, but
it's the same one, but
first,
that one is with colors and that one is with the distance, like
the arrow means that I can model the reversal with edits that are 2 times as many.
No, the other way around.
Okay.
If you have edit distance k, then you have reversal distance 2k.
Okay. It seems to me
at most 2k.
You could swap do by a reversal. By 2 reversals, I can do 1 swap.
Yes.
Yes, because you can do swaps by edits and edits by reversals.
It's 4K, but yeah, we omitted some of the. It's like Hasse diagram, so we don't introduce extra arrows which are already implied by something else, even though we could improve.
You don't care about the constants.
Yes. We only care about there is a relation or there is no relation.
Okay.
Any other question? That's it from me. Thank you.